Waveguides Dispersion Characteristics series on microwave engineering, lecture number 1.50. Waveguides are dispersive in nature. Dispersion means wave velocity being dependent upon the wavelength or frequency of the wave. In the present session, we try to explore the dispersive nature of waveguides. Now, let us move further in this endeavor. Transmission media can be divided into two groups: dispersive, non-dispersive. In dispersive media, velocity of the wave traveling through it depends upon frequency or wavelength. In case of non-dispersive media, velocity is frequency independent or wavelength independent. In dispersive media, not only velocity, other quantities like wavelength measured along the length of the guide and impedances like wave impedance, characteristic impedance, they also vary with frequency, whereas in dispersive media, wavelengths or impedances, they are frequency independent. Parallel plate guide and hollow pipe waveguides, they fall in the category of dispersive media, whereas parallel wire transmission lines, coaxial cables, free space, these are all the media that belongs to the second category. Here, briefly, the dispersion characteristics of guides, they are shown. Phase shift constant beta, bar is there over it. This bar, it indicates that phase shift constant is measured along the length of the guide. Similarly, guide wavelength also, bar is there. It is placed over its head. It indicates that wavelength is measured along the length of the guide. Phase velocity, bar is there. This bar indicates it is measured along the length of the waveguide. Group velocity. You can see here, for example, phase shift constant. At frequency is cutoff frequency, phase shift constant is 0, but when frequency is very high, it is non-zero, equal to omega root mu epsilon. Guide wavelength at cutoff frequency, it is called indicated by lambda bar, right? F equal to Fc, cutoff frequency, it is infinity. But when frequency is very high, it is the 2 pi by omega root mu epsilon. Phase velocity at cutoff frequency, it is infinity, but at high frequencies it is 1 by root mu epsilon. Group velocity is 0 at cutoff frequency and it is equal to V, that is 1 by root mu epsilon when frequency is infinity. Here the important point to note or to observe is that their values, phase shift constant value, guide wavelength value, phase velocity value, group velocity value, they are varying with frequency. At cutoff frequency, they are assuming certain values. As you move towards higher frequencies, they are also moving towards different values. So, velocities, wavelengths, they are changing with frequency. That's why these are all considered as dispersion characteristics. The waves that are carried by dispersive media, they are called dispersive waves. TE, TM and hybrid waves in guides are examples for this category. Already it is known to us pretty well that TEM wave, electromagnetic wave, can be divided into two categories: TEM, non-TEM. Under non-TEM, we have TE, TM, TE plus TM. This TE plus TM is also sometimes called hybrid wave or mixed wave. Non-TEM waves, TE, TM and hybrid waves in guides, these all can be grouped under non-TEM waves. So the waves, non-TEM waves, they exist in dispersive media and these waves are called dispersive waves. Waves carried by non-dispersive media, TEM waves, they are called non-dispersive waves. Waves in free space, waves in coaxial line, waves over transmission lines, these are all examples for non-dispersive waves. Of course, they all belong to the category of TEM waves. Under dispersion characteristics, normally we study guide wavelength, phase velocity, group velocity, all the three. We are going to see, once you have an expression for guide wavelength, obtaining an expression for phase velocity or group velocity is quite a simple mathematical process. Obtaining expression for guide wavelength is also a simple process, but the starting point is, first we obtain guide wavelength from characteristic equation and from that phase velocity and group velocity. Here, of course, we are going to first define guide wavelength, phase velocity, group velocity, and then try to obtain expressions for this quantities. Now, a definition for phase shift constant. The phase shift constant indicates phase change per unit distance along the guide length. It is denoted by beta bar. In general, actually this bar, as already mentioned, this bar indicates or it tells that it is measured along the guide length. Along the guide length, it is indicated by a bar mathematically. In general, beta bar is 2 pi by lambda bar. Again, lambda bar means wavelength measured along the length of the guide. It is called guide wavelength. Anyway, this constant is useful mainly because all the three parameters to be discussed under dispersion characteristics are defined in terms of this particular one. Beta bar equal to 2 pi by lambda bar. Here, one point I want to tell you to give certain clarity regarding beta. Beta is, it has a name, it is phase shift constant. Its units are either degrees or radians per unit length meters. Definition of beta is phase shift the wave undergoes by the time it travels a distance equal to 1 unit, or phase shift the wave undergoes when it travels 1 meter. By the time it travels 1 lambda, the phase shift it undergoes is 2 pi. Lambda is wavelength, the corresponding phase is 2 pi. So beta is phase shift per unit length. Phase shift for one wavelength is 2 pi. So phase shift per unit length becomes 2 pi by lambda. So beta is, from the definition, it is 2 pi by lambda, from the definition. If wavelength is measured along the length of the waveguide, then beta becomes phase shift constant along the length of the guide. So this definition, this is from the defining definition of beta. Right. Now here we try to derive an expression for beta bar. We know gamma bar, phase propagation constant is equal to under square root h square minus omega square mu epsilon. This is called characteristic equation. This characteristic equation is valid for parallel plate guides, rectangular waveguides, and also circular waveguides. Now we can see this is a complex quantity. It has a real part, it is and also imaginary part. Real part is attenuation constant, imaginary part is phase shift constant. Now, depending upon the frequency, it may be real or it may be imaginary. Here, there is no scope for complex values for omega, for gamma. Depending upon omega, when omega is small, gamma is real, alpha. When omega is very large, gamma is J beta. In general, of course, gamma is alpha plus J beta. But in this situation, for this situation, which is under consideration, gamma is either alpha or beta. Now, we are considering wave journey inside the guide. Therefore, wave is traveling. So, beta is not 0. So, alpha is 0. So, in the present case, as we are considering a wave already inside the guide, alpha is 0. So, gamma is J beta. From this, beta can be found. So, beta is omega square mu epsilon minus square. H, you know, it is cutoff. It is called cutoff wave number. Its value depends upon the configuration, guide configuration. For parallel plate guides, one expression. For rectangular wave guides, one expression. For circular wave guides, some other expression, different expressions. But in all the cases, H square is equal to omega c square mu epsilon. So from this, a little bit of manipulation, it leads to omega root mu epsilon square root of 1 minus fc by f whole square, or omega mu epsilon multiplied by f. Here f is square root of 1 minus fc by f whole square. It's a fact. Once beta is known or beta bar is known, remaining things we can, as already mentioned, they can be very easily derived or found. Now we consider guide wavelength. What is guide wavelength? The definition is there. 3-4 equivalent ways of defining the wavelength is available. All are given here. It can be defined as the distance corresponding to one cycle of variation of field configuration in the axial direction of the guiding system, or the distance between two consecutive equiphase planes along the length of the guiding system, or the distance that a wave travels down the guide while undergoing a phase shift of 2 pi radians. These are all same, but putting the things in different words or different format. Mathematically, it is indicated by lambda bar or lambda g. G indicates that it is measured along the guide. It is lambda bar is 2 pi by beta bar. Actually, I want you to remind beta. What is beta bar? Beta bar is 2 pi by lambda bar. So therefore, lambda bar is 2 pi by beta bar. So now we have expression for beta bar. Already we have derived that beta bar. You substitute 2 pi by beta bar. Substituting beta bar, that expression for beta bar, then with a little bit of manipulation, we have lambda naught by square root of 1 minus lambda naught by lambda c whole square, which is equal to lambda naught by 1 minus fc by f whole square, which is lambda naught by f. F of course f is this factor and lambda naught is v by f. The interrelation between lambda g guide wavelength, cutoff wavelength, lambda c is cutoff wavelength, guide wavelength, cutoff wavelength and wavelength, the ordinary wavelength. This ordinary wavelength is v by f. This is there is a relation. This relation is also well known. The connecting relation between guide wavelength, cutoff wavelength and ordinary wavelength, it is a well-known relation. That's why it is being mentioned, and this relation is derived from this relation. Before moving further, I want to notice the fact that what is lambda naught? Lambda g, you can understand, already defined. It is wavelength measured along the length of the guide. Cutoff wavelength, you have already seen while discussing about filter characteristics, the definition and all that. And what is lambda naught? Lambda naught is v by f. Okay. V means 1 by root mu epsilon by f means 1 by f. When the hollow region is a free space, of course 1 by root mu epsilon becomes c. V becomes c when hollow region is free space. Otherwise, it is V is c by root epsilon r. Otherwise, in ordinary cases, I want you viewer to notice this particular point. Now, velocity, wave velocity or phase velocity, it is defined as the velocity at which the phase of the wave changes along the length of the guiding system. It is more than or equal to the unbounded medium velocity, which is V equal to 1 by root mu epsilon. If hollow region is free space or air, then V becomes C. As already mentioned, this is one of the three quantities that are discussed under dispersion characteristics. To give some clarity regarding wave velocity, guide wavelength, here a pictorial representation of wave journey inside the waveguide is shown. Notice the wave journey is not straight from one end to another end. It is not straight. Its travel is in a zigzag path like this. First it travels, hits the side wall, gets reflected, again hits the side wall, again gets reflected. So journey is hitting and getting reflected, hits and reflections. While hitting and reflecting, it travels from source to the destination. Now consider wave journey before hitting the side wall. If you consider two equiphase planes having a phase difference of 2 pi, the distance by definition between them, if measured along the direction of journey, it is ordinary lambda, wavelength. But wavelength can also be measured along the length of the guide, because see, consider these 2 points. These 2 points are also having a phase difference of 2 pi. Hence, the distance between them is qualified to be called wavelength. But this wavelength is different from the wavelength that is measured along the direction of the journey of the wave. So this length or wavelength are the distance between the points which are identified along the length of the guide. This distance is called guide wavelength. So in this way one can easily understand the difference between ordinary wavelength and guide wavelength. Ordinary wavelength is wavelength measured along the direction of propagation of the wave, whereas guide wavelength is the distance measured along the length of the guide. These two are related. Of course, that relation I have already shown. Now, one more point. This lambda is free space wavelength when this medium is a free space. Otherwise, it is lambda naught. Right. Now, with this wavelength, considering this wavelength, considering guide wavelength, one can measure the velocity. That velocity is phase velocity. This is velocity of the wave inside the guide. This velocity is 1 by root mu epsilon. Of course, this is equal to f into lambda, this velocity. You can consider velocity along the guide length also. This velocity is called phase velocity. This velocity is frequency times guide wavelength, lambda bar. Here you can find guide wavelength, phase velocity, and wavefronts, all those things. The idea is to give you a picture of useful for visualizing various aspects of wave journey inside the guide. Mathematically, this wave velocity or phase velocity, it is indicated V bar or Vp, it is omega by beta bar. By definition, it is omega by beta bar, and beta bar we have already have expression. Substituting beta bar here and noting that omega is 2 pi f, we can do a little bit of manipulation to get these expressions. Ultimately, in a short form, V bar becomes V by f. As already mentioned, V is 1 by root mu epsilon. Group velocity, last one is group velocity. Definition is, it is the velocity with which a narrow band signal or a group of frequencies intelligence travels in the guide. It is always less than velocity of wave in the unbounded medium. If hollow region is free space, of course V becomes equal to C. Here I want to remind you, phase velocity is more than velocity of wave in the unbounded medium, whereas group velocity is always less than velocity of the wave in the unbounded medium. Mathematically, Vg, it is indicated as Vg, it is equal to d omega by d beta. This is defining relation. Vg equal to d omega by d beta bar. But we have expression for beta bar. By differentiating that expression and after doing a little bit of manipulation, you get like this. Notice the expressions for phase velocity. In the expressions for phase velocity, you have V by, but here it is V multiplied by f. Okay. So this is all that is I want to share with you for now.